Okay. Let's start here. We haven't finished this problem yet. Some of you are a bit slow getting your notebooks out. Here's something that I was hoping would have come up just in the discussion. It hasn't quite come up yet, but here was the issue that we were having, if you remember from, when was this, Tuesday? What does this side have that I'm circling that this side does not have? Look closely. C. C is right here, no C over here. Correct?
Yeah.
Well, how does it all of a sudden disappear?
We erased it. Found the derivative.
We isolated C, because what is C?
Constant.
It's a constant. If you take the derivative of a constant,
It's 0.
it's 0. So hopefully, what I was hoping would have happened is realize, hey, there's no C over here, but the only way to get rid of C is to take the derivative of it and make it 0. So we had to isolate it before taking the derivative, which is what we eventually came to, but we ran out of time. Does that make sense? Why?
Yeah.
We need to get C by itself because when we differentiate both sides, the derivative of C is 0. Why do we want C to go away? Well, because it's not over here. There's no C over here. Okay? Anyway, let's finish this up and move on. So we took the derivative. Okay? This was a quotient rule. We had to do a quotient rule from this.
Oh dear.
This was just y prime. Okay, and the derivative of C is just 0. But we're supposed to isolate y prime. Oof.
How many times y squared over the y prime?
Wait, wouldn't the derivative of y be dy dx?
Yeah, it's just y prime.
Oh, yeah, that's right.
Yeah. All right, suggestions.
Well, we can subtract, or we can, subtract.
Wait, hold on, Braden. We had a suggestion. Then I'll come back to you. What were you saying? Oh, you were going last time. Okay. We're trying to get this into this. We're trying to verify. So we're trying to turn this into that. We tried it once here. We didn't get anywhere much with that. We didn't get very far with that side. So we went a different route.
Do you want to times y squared over and then leave y prime on that side?
Okay, that's a good suggestion. There's a problem with that, though.
Because it's being added by y prime.
It's because we're being added by y prime, so we can't just multiply the y squared over here yet.
So you have to minus the y prime.
That's also not a bad suggestion. I mean, we could subtract the y prime over here.
We subtract
The problem is, you guys, we have two y primes. We have one right here and one right here, obviously. If we separate them and get them farther apart, then we're going to be further away from the goal. The goal is to try to combine the y primes into one y prime. Let's say that again. You're really, really close, except this term here doesn't have a y prime, so we can't pull it out of there. But that's eventually the route we're going to try to head, is to try to factor out a y prime from something.
Do we try to add the y prime in?
Let's see if we can combine that. You guys follow?
Yeah.
Let's see if we can combine that into one expression. So what does this side need so that we can add them together?
Y squared.
Y squared over y squared. So now we have y times 2x minus x squared y prime plus y prime all over y squared.
With the y
And that equals 0.
multiplied by y squared, and
Oh, yeah, sorry, y squared right there. Don't want to forget about that. Y squared over y squared to get a common denominator. Then we added them together. Okay, now we can start the ball rolling. This should go pretty quick from here. Let's keep this moving. We got to move quick.
Now you're trying to y squared over.
Can we?
You can.
Okay, here's the thing, you guys, and I've brought this up before, and it's quite often forgotten. This is a fraction, yes or no?
Yeah.
The fraction equals 0, yes or no?
Yes.
How's that possible for a fraction to equal 0?
If the top equals 0.
If the numerator is equal to 0, so we have y 2x minus x squared y prime plus y prime y squared is equal to 0. Okay, let's keep going.
That.
so now we can add terms across.
Keep in mind what we're trying to get it into. We're trying to get it to look like this.
So we should get all the y prime terms on one side and all the non-y prime terms on the other side.
Exactly. You guys have seen this before. This is similar to implicit differentiation, where we want to get the dy dx's on one side, all the non-dy dx's on the other side. Does this sound familiar?
Yes.
So which one moves?
Uh,
The y2x moves over here, right?
then we can
So we've got negative x squared y prime plus y prime y squared equals negative 2xy. Now we can factor out a y prime. We've got y squared minus x squared equals negative 2xy. And divide, so y prime is equal to negative 2xy over y squared minus x squared. And oh, we might have it. We're supposed to make it look like,
Yeah.
oh crap. So if we factor out a negative from the bottom, didn't that turn into x squared minus y squared over negative 2xy? You following? Now the negative sign cancels. And we have 2xy over x squared minus y squared. Holy mother of whatever. That took some work.
I don't know. Is there a shortcut for this? I don't know.
Just getting better at it. That's the shortcut.
There's no shortcut. I like the shortcut. Someone didn't do better. Just like tonight?
You like to go play? We tend to play.
I think I would.
We didn't do much with trigonometry. Let's do one more trig one. Determine whether the function is a solution to the differential equation xy prime minus 2y equals x to the third e to the x. Back. Oh.
Whoa. Opposite of the hypotenuse.
So determine whether this function, determine whether this function is a solution to that differential equation there. So these are yes or no answers. Look, go back in your notes. Let's take a look at the first two examples. Flip back in your notes.
How far back? This chapter?
Over the sign.
Sign after sign. Yeah.
Okay, this was our first example, right? Hey, we focused. Come on. Look back at the first example. Gabe.
Yes, sir.
We had this was example 1. We had a second order differential equation. We had to verify that this was a solution. So first we had to find y double prime. Okay. And then we just substituted in. Y double prime minus y was 4e to the negative x minus 4e to the negative x. It was equal to 0, and that's what it should have equaled. Y double prime minus y was equal to 0, so we verified it. Now that verify means this really is a solution. You just have to show it. We don't know whether this function here, where'd it go? This one. We don't know if it's a solution or not. We have to verify it. What would you suggest?
I would suggest that we multiply x by both sides. Never mind.
What's y prime?
Y prime is cosine.
Yeah. Y double prime is negative.
It is negative sine x, but we might not need that.
So we can plug sine x for y and cosine x for y prime.
Yeah.
It's all for it.
And we can manipulate it until we figure out what x is.
Well,
Straight up.
it says determine whether the function. It might be no. This might not be a solution. It might be. So, what are your suggestions? What should we try?
So we're just trying to get this equal to zero.
No, we're trying to get this.
I would, wait, can we manipulate the top equation?
I'm confused just on what I'm supposed to do. I'm supposed to be
If
input
we-
those in that main equation or taking.
That's what we did. Look back at the previous examples here. Go back to your notes again. How did we verify this? How did we verify that this was a solution of that?
You plug it in and it equals 0.
Yeah.
We found what y double prime was. We already knew what y was. We plugged them into this. Down here, we plugged y double prime. We plugged 4e to the negative x. We plugged in minus y. That was 4e to the negative x.
Alright.
And we showed that that was equal to 0. So we didn't really have to do anything to this other than plug things into it,
Yeah.
the differential equation. We had to mess with the given function. Okay?
Wait,
So
we
here-
can't mess with the verifying function.
Here we've been given a function.
Yeah.
Okay? And then we found y prime.
Yeah.
So we plug these in.
Now it's
We're supposed to try to show that this is a true statement. If not, if it is a true statement, then it is a solution. If it's not a true statement, it's not a solution.
ooh,
Okay.
we could use some.
So what's y prime?
It's cosine x.
Okay? Minus 2.
Sine x. Mhm. Huh. Oh. Well, we could.
I said no.
Let's see. cosine x.
Are we seeing anything? First of all, I mean, if it deals with trig, it might be some trig identity.
Yeah,
But
how do you get dx? I mean, if you get ln if you found the integral somehow.
I'm not seeing any trig identities. Anybody seeing any trig identities?
I'm not seeing.
If it were sine squared and cosine squared, that would be something, but it's just sine and cosine.
We could change those to
I think some of you might be overthinking. It might just be no, it's not a solution. Is there anything that we see?
I want to change it to cosecant and secant. See how that changes the problem.
So we might be overthinking this, you guys. Does it look even possible to make this side equal to that? Not very likely.
APX, you can't make any trig function.
So
kind of make a trig function and have an ln.
don't overthink it, you guys. It would just not be a solution.
I can't believe
Okay?
Okay.
you took that 50 on how you rock that.
Let's find another particular solution.
Find a particular.
Okay. Y equals CE to the negative 2x. Two parts to this problem. Verify this, meaning that equation is a solution to y prime plus 2y equals 0.
Okay.
Then find particular solution when y equals 3, x equals 0. So after you've verified, find the particular solution. When you see that phrase, find the particular solution, that means find the value of c. Right now c is any constant. And you can still use c as a constant when you're verifying it. Once you've verified it, find the particular solution by plugging in the y and the x value. That's to find c. Did we get it?
So are you plugging in the CE to the negative 2x, or 2 times CE to the negative 2x,
Alright,
and then the y prime, and then you're plugging in the x's, or,
You take this and plug them in here.
and then you plug in the x's for the particular?
Once you've verified it, then you plug in for the particular into this.
Oh, into the original.
This now makes sense.
Because this is the solution. We just got to find out what c is.
Oh, okay.
What is y prime?
Y prime equals negative 2c e to the negative 2x.
Okay, check it out. Shh, 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 shh. Where does negative 2 come from?
The chain rule.
Chain rule. Right, Hayden?
Yeah, that's what I was thinking.
Okay, this is a chain rule. This is a chain rule. We have to do a negative 2 because of the derivative of that exponent. So now plug it into the differential. Y prime is negative 2 c e to the negative 2x plus 2 times y. So that's 2 c e. And what's that supposed to equal?
0.
Does it?
Yeah,
So we verified it. So this is a solution.
I'm gonna put a check.
Now that we know that, we can use the initial conditions here, plug it into the solution to find a value of c. So the solution was y equals ce to the negative 2x, but now we have a value of y and x. Okay? Y is 3, and x is 0. What's e to the 0 power? 1. So c equals 3.
C.
So the particular solution is y equals 3
e to the negative 2x.
Negative 2x.
I like that one.
It was a lot easier than the other one.
Yeah, that other one was quite confusing.
I didn't like it.
I think you guys were overthinking that last one, and sometimes the answer is just no, it's not a solution. What's that? Because e to the 0 power is 1. And then 1 times c is just c, so c equals 3.
Alright.
Okay? Let's try this. Let's try this one more time now. Determine whether. Let's try this one more time. Determine whether the function. So this is a yes. This is another yes or no. Either yes it is or no it's not. And let's not overthink it. The function y equals x squared e to the x is a solution. And let's use the same differential equation. xy prime minus 2y equals x to the third e to the x. So it's the same differential equation. We just have a new potential solution here. This might be a solution. This might not be a solution.
So we've got to put our thinking caps on.
So we know that y equals x squared e to the x. We don't know what y prime equals yet. It's not a chain rule. It's a product rule. So what's the product rule?
It is FDG plus BGF.
Don't say it like that.
2x e to the x plus x squared e to the x. So there's y prime. Okay, so let's make the substitution now. Take both of these, take this, and take that whole thing, plug it into the differential equation. Let's try to verify both sides. So we're going to have x times 2x e to the x plus x squared e to the x minus 2. And you just plug in your y, that's x squared e to the x. Let's first just figure out what that equals. So this is 2x squared e to the x plus x cubed e to the x minus 2x squared e to the x. I just distributed the x there. And distributed, well, there's really not distributing the negative 2. Just multiply the negative 2 with x squared e to the x. What happened there?
Cancel each other.
This cancels that, and we have x cubed e to the x, which equals x cubed e to the x. It equals what it's supposed to equal, so is that a solution?
Yes. This is like identity.
So y squared, or y equals x squared e to the x is a solution. Okay. We've got to move on to slope fields. I got to try to draw some of these. This might take just a second. Very small ones. Still same lesson. Slope fields. So, on a very small scale, extremely small scale, you're going to have to draw your own slope field. So sketch. Oh, you can't see. Sketch a slope field. For the differential equation y prime equals x minus y. For the points negative 1 comma 1, 0 comma 1, and 1 comma 1. So on a very small scale, you'll be drawing this slope field.
How small can you really draw a slope field?
Well, you've seen the slope fields before in your homework. They've got a bunch of little lines everywhere, right? You've only got to draw 3 here. You've only got to draw 3 little line segments because there's 3 points. Okay, those slope fields, you know how they have those little teeny line segments? Those are slopes at individual points, and they have 20 or 30 little teeny line segments. That's the slope at 30 points in a function. You've only got to draw slopes at 3 points, so it's just 3 little teeny line segments. You guys follow?
Yeah.
So this is just a small scale of a slope field. The ones that have those 20 or 30 little segments, those will already be given to you. You don't have to draw those. That would take forever.
Okay, good.
Okay? So as carefully and as neatly as you can, draw a graph, and then make sure the axes are scaled the same distance. Okay, now, you guys know this. I know that you know this because you've said it a billion times. What's one thing you can use a derivative for? Finding a slope, but only if you have points. You guys following? This is a derivative, yes or no? So what can this give you? This can give you slope, but only if you have, but guess what we have? So it's not as hard as you think. If you plug in this x and y to this x and y, that's going to give you y prime equals a number. If y prime equals a number, that's a slope. Okay? So let's do this y prime.
Are you sketching a bunch of slopes? Yeah.
That's what a slope field is. It's a bunch of little slopes at individual points. So y prime at negative 1 comma 1. Y prime at negative 1 comma 1. Well, y prime is equal to x minus y. So this is negative 1 minus 1, which is negative 2. So what you do, you guys, is you go over to negative 1, positive 1, okay, and you just draw a little teeny line segment of your best estimate of a slope of negative 2. Okay, is this a slope of negative 2? Why not? It's positive, right? So it'd have to be at negative 1 comma 1, just a little teeny line segment that's your best estimate of a slope of negative 2, something like that. You guys follow? Now do the same thing. Let's do y prime at the point
0, 1.
0, 1. That means y prime is equal to 0 minus 1, which equals negative 1. So at 0 comma 1, it's still a negative slope, but it's just not quite so steep as the one. You following?
Yeah.
So it's just a little line segment that has less of a steep negative slope, maybe something like that.
0.
Lighten up your attitude.
Okay, now
Change your attitude, change
y
your life.
prime at the point 1 comma 1. Y prime equals 1 minus 1, so that equals
0.
0. So at 1 comma 1, you just have a little teeny line segment that's flat.
I think here that dot is supposed to go to negative 1.
That's all you do?
That's possible.
For that equation?
If
Or for that
if they
field?
ask you to sketch a slope field at just a couple of points, that's a slope field at a couple of points. The slope fields you guys are used to seeing in your homework are slopes at like 30 points, and that's
Oh,
not something you'd be expected to do by hand,
okay,
Okay.
that's good.
because they only wanted 3 points. If they wanted a few more points, you'd do a few more. This is something that you guys are probably going to want to get at some point before the AP test. It's one of the programs I've given it, I think, to some of you. AA Calc 1. So if you run the program, the fourth option here is a slope field. Okay? Check it out. Y prime equals x minus. Where's y? Y prime equals x minus y. Now I'm going to choose my x max. X min is negative 3. X max is positive 3. The x scale. So the calculator can generate the slope field for you. Okay.
Oh wow, that's cool.
Take a look. The ones that we drew was this one here. This was negative 2. This was negative 1. And that was 1, 1.
Why doesn't it show a string?
Okay.
Actual graph?
I don't know where the axes went. I'll have to take a look at that. Okay. Alpha, and then the number 1. Alpha 1. Okay, so you can have your calculator draw a slope field for it.
Wow, that's cool.
No, you're not going to make one. They're going to give you a picture, okay? And somewhere in the picture there's going to be, let's say, 2, 1 right here. They're going to give you a particular point at 2, 1. And they're going to want you to estimate the solution that goes through that point. A particular solution. Okay? Now, you guys, what generated this slope field? What is this? What's the name of this kind of function?
A derivative function.
Yeah, differential
Equation.
Okay, I need you guys to understand this. What generates a slope field?
A differential equation.
A differential equation. Let me ask it again so that everybody hears it, Gabe. What generates a slope field? A differential equation. What have we been doing with our differential equations? We've been finding solutions. Some of them were general solutions involving C. Some of them were called particular solution. I need you guys to understand the terminology here. Let me repeat it. What generates a slope field? What can you do with differential equations? You can find general solutions or particular solutions. Okay, the slope field in a way, you guys listening carefully, the slope field in a way could be considered the general solutions. It's all the general solutions that could happen. Okay? If you want to use the slope field to find a particular solution, you have to have what? A point. You have to have one point to find a particular solution. You guys following? So on this picture here, where did it go? On this picture here, the general slope field just represents the general solutions to a differential equation. Yes?
Yeah.
If you locate a particular point, you can then start to sketch a particular solution by following the slopes of the line of all these slopes through it. Does that make sense? So going through here, you see how that curve follows the slopes of those lines in between? And if you continue it to the left, if you follow the direction of the slopes,
I like it.
in a way, okay? What would you call that, though? The line I drew in
A
black?
parabola.
Well, all of this slope field is a general solution, but this one I've drawn here would be a particular solution through that point. You can use the slope field to kind of sketch a particular solution by following the slopes. Okay? No. We wouldn't be able to come up with this equation. We would just have to have the estimate of this using the slope field. So this is what you guys would be expected to do on your homework, is given a point, estimate the solution by following the slopes through those points. That's about it. You would never be expected to draw all of these little slopes. That would be... Okay? Okay? Pretty easy. Okay, guys, stand up.
Look, Steve, this is what we do.